My name is Demidov. I work for Supercomputer Center of Russian Academy of Sciences, and today I'm going to talk about VexCL, the library I developed, and basically how it works. Okay, so I'll start with a bit of an introduction. So today, if you want to use GPUs for scientific computing, you have basically two main frameworks that you can use. It's either NVIDIA CUDA or OpenCL. And in many ways, they are very similar, but there are some differences. So CUDA is a proprietary architecture by NVIDIA, and it obviously only works on NVIDIA's hardware. And OpenCL is an open standard which is supported by many hardware vendors, AMD, NVIDIA, Intel, many niche hardware products. So, but NVIDIA was much more active with the marketing, with promoting community evolving around CUDA. So CUDA currently has more libraries. It is kind of more mature, but yeah, and the drawback of OpenCL is that the amount of boilerplate code that you have to write to even get the GPU started is much more than with CUDA, especially with CUDA runtime, if you're not talking about CUDA driver API. And also in CUDA, kernels are written in C++, so you can directly use some metaprogramming techniques with CUDA. And in OpenCL, kernels are written in almost, C99. Okay, so no templates, no metaprogramming at all. But the other difference is how the kernels, the compute kernels, the functions that work on GPU are compiled. So with CUDA, kernels are compiled to this pseudo assembler language, PTX, at compile time of your host program. And with OpenCL, kernels are compiled at runtime. So you call some API functions and you compile your kernels and then you run them on the GPUs. And usually this distinction is considered to be OpenCL drawback because it takes more time to initialize your program. But it also allows you to generate more effective kernels at runtime, which are specifically suited for your current needs. And VexCL is providing you this ability. Okay. So what is VexCL? VexCL is a vector expression library. It's a header-only C++ library which was developed to help you. Well, initially it was developed to help me to reduce the amount of time that you need to invest to develop a GPU program. And it provides you convenient MATLAB-like notation for vector expressions, and it generates OpenCL or CUDA code at just in time and executes it. And it makes it, in my view, much easier to work with GPUs. Okay, and the source code is available under liberal MIT license on GitHub. So just to give you the short overview of VexCL interface. So here is the minimal program written with the use of VexCL library. So first we include this header, VexCL, vexcl.hpp. Then we initialize VexCL context with a device filter, and every compute device that satisfies this filter, in this case, every compute device that supports double precision, will be grabbed for this context, and you will work with the devices later on. Then you allocate some vectors on GPU, you move some initial data into the vectors, and then the primary magic happens in this line. You write a C++ expression which will get automatically, which will generate a compute kernel automatically, which will compile it for the GPUs you selected, and which will execute the kernels on the GPUs you selected. Okay? Then you can get the result back to host and do some interesting things with it. Okay? So initialization is you initialize the VexCL context with the device filter, which is just a functor which takes reference to a device, to a compute device, and it either returns true or false, depending on whether you want to use this device or not. you can combine the filters with logical expressions, and then you just get a more fine-grained control over the devices which you want to use. Okay, and when there is only one device, then obviously all vectors are going to be stored on this device. But when you have more than one devices, then vectors and accordingly the work on the vectors are split in the same way across all devices. So if you don't, if your kernels are embarrassingly parallel, you don't need to do any exchange between the devices. Okay, and this split by default is performed in proportion to the device bandwidth, but you can control that as well. So what vector expressions are supported? So first you have to make sure that the vectors in the expression are compatible, and that means that they should have the same size almost in every case, and they should be located on the same devices. And then you can combine the vectors with all C++ overloadable arithmetic logical operators, and you have some parallel primitives as well, like sort, scan, fast Fourier transform, matrix vector products, random number generation, etc., etc. And you can combine these expressions in much more complex expressions as well. So here's a bit more involved example. Imagine that you want to compute an approximate value of pi with a Monte Carlo experiment. And this can be done with use of these qualities. So if you have a circle inscribed in a square, then the pi will be equal to 4 times the fraction of area of circle to area of the square. And we can approximate that if we put a lot of random points inside the square. We can approximate the area of circle to the area of square by number of points that got into the circle to number of points to the total number of points. Okay, and you do this with this simple expression. So you start with the element index of your vector element. So it's just the position of the element inside the vector. Then you feed this expression into this random number generation function. This is lazy function. Then you get the two-dimensional point out of it, and you compute its magnitude. So the distance from the center of from axis origin to this point. And then you see if this distance is actually less than 1. And then you sum this expression, so you get an amount of points that got into this square of radius 1, or circle of radius 1, okay? And then you just multiply it by 4 and divide by n. And this whole expression will result in a single kernel, just tailored for this particular task. And yeah, it also will be very effective because no global memory on the device is touched here, because these random number generators in VexCL are stateless, they're counter-based. So it's just, this problem will be compute bound, okay? So it will work really fast. And so how does it, how does it look if you look into the generated kernels? So for example, this expression, when compiled with switch, the compile time switch VexCL backend OpenCL, or just by default if you don't provide the switch, will generate, compile, and launch the following kernel at runtime. So you see this expression will result in this almost identical expression here, and the leaves of the expression, terminals, will become parameters of the kernel, and it's all handled automatically. Okay, and if you change this switch to VexCL backend CUDA, it will generate CUDA kernel. It will compile it at runtime again, and run it on a CUDA capable device. So the question is, how does it work? And this is the topic of today's talk. How can the library does this? And in 2 words, the answer is expression templates. And the idea of expression templates is quite old. It was proposed in '95 by Todd Veldhuizen in his C++ report, and it also was implemented by him as well with, in his Blitz++ library. And today, many libraries use this technique. For example, Blaze library is in the popular track now. The author of Blaze library, he is probably telling some of the same things. So maybe it's a good thing that we share the parallel track with him. So, but yeah, how does it really work? And to give you an idea, this is a simple example. Imagine we want to do a vector arithmetic, and we, for the time, forget about the GPUs. We just want to do it on the CPU. So we want to be able to write this expression, and we want it to be as effective as a handwritten loop, okay? And the obvious idea is, of course, wrong, as it happens with many obvious ideas. So if we just overload a plus operator, which will take two vectors, create temporary vector, fill it, and return it as a result, it will work correctly, but it will not work efficiently. And the problems is we have extra memory allocation, which is not really that big problem because it's constant and it will be hidden if you have really large vectors. But also we have extra memory I/O because, for example, in this expression we have two temporary vectors because we have two operations, sum operations, and for each of them we have create a temporary vector. And we also have 8 memory reads and writes for each vector element. So here we have to create temporary, read this vector, write temporary, read temporary back for this operation, read X, write another temporary. Then for the assignment, we have to read the result and put it into the actual result, right? So 8 memory reads and writes. And with modern computers, memory is the biggest bottleneck. So, for example, with this manually written code, it's just, yeah, there is no temporaries, and we only have 1, 2, 3, 4 memory accesses per each element. So it will be about twice as fast. So the idea is very simple. Let's postpone the actual evaluation of the expression until assignment, okay? So we create this simple struct, which will hold references to operands of the operation. And then we, for the addition operator, we will just return this struct. So we'll return a record that we would like to add these vectors at some point in the future, but we do not do any work here, okay? And the actual work is performed in the assignment operator, so which takes this struct, which is just tells us that we would like to add this vector and get the result and assign the result to our internal data struct. Okay, so we just iterate over all elements and we take left-hand side vector, we take right-hand side vector, and we add them together, okay? So here there is no temporaries, and the memory access is as efficient as with handwritten code. Okay, but the problem is it's not composable. So if we write a more complex expression, compiler will not like it because the result of the first operation is vsum, and compiler doesn't know what to do with vsum and the vector. Okay, so we have to do it more composable, and in order to do that, we now templatize the struct. So it has now template parameters, the type of the left-hand side, the type of the right-hand side class, and we hold references to these operands, and we also provide an indexing operator, overload of indexing operator, which just returns the ith element of left-hand side summed with the ith element of right-hand side. Okay, the addition operator is as simple as before. It just has to take care of these template parameters, and the assignment operator is slightly changed. We have this now. We ask the expression to provide its ith result for us. Okay. So the problem with this is that we're still constrained by addition. And we would also like to do sometimes the multiplication, division, etc., etc. So let's add another layer of generality. We provide this struct plus and minus and divides and any other operations we would like to do. And it just has a static method which takes 2 arguments and returns whatever operations should be made on the arguments, okay? And then we make this vSum struct, we rename it to binary operation, and now it has 3 template parameters, left-hand side, right-hand side, and operation to be done with them, okay? And we still provide this indexing operator. Now we do not call the plus explicitly, we just delegate the work to this operation struct, okay? Yeah, and yeah, this is for addition operator, we just return a binary operation between left-hand side and right-hand side with a plus operation. And we provide similar overloads for all other binary operations. So the expression templates, and this struct binary operation is called expression template because it just encodes the expression that you got out of a C++ compiler, right? They are in fact trees because the expression in the right-hand side of this assignment operator has the binary operation between vector, and they should be added. And if you subtract z from this, then it will be binary operation between that binary operation and another vector, and the results should be subtracted. Yes, so we have a tree of this form, and when we assign this tree to a vector, we just iterate over the tree, and this indexing operator just propagates downwards until it meets the actual vectors, and then it's as effective as a manually written code. And you can even do some other things hidden from the user. For example, you can add pragma OMP parallel here, which will be hidden inside the assignment operator. So users will know nothing about OpenMP, but they will use now all cores of your multi-core processor. And yeah, so basically the C++ compiler walks the tree for you at compile time, and it uses indexing operator of this binary operation and of the actual leaves to do the work. Okay. So far so good. So now you should understand what expression templates are. So we are now able to write these expressions or expressions like this, and this should be as effective as manually written code. Okay. So there are no temporaries, and if you and optimizing compiler, since it walks the tree at compile time, it can inline everything for you, and it's very effective. But how is that related to OpenCL code generation, right? Let's talk about this. So how does OpenCL work? And I will, for the rest of the talk, I will only talk about OpenCL, but the CUDA backend is implemented in almost the same way. So there is no difference. So in OpenCL, the compute kernel is compiled at runtime from a C99 source code. And then you set kernel parameters through some API calls, OpenCL API. Then you launch the kernel on a compute device, you put it to an execution queue. And this source code may be read from a file, it may be read from a static string, or it can be generated at runtime as well. So if we have an expression of this expression, then the terminals of the expression should become kernel parameters, and the expression itself should generate a string like this, which we can just assign inside the kernel to the result, to the output parameter. So, and we can just do the same thing that we did with expression templates on a CPU code. We can delegate the work to the actual terminals. For example, each terminal knows what parameters it needs to declare inside the kernel. For example, vector has to declare a global double, well, if it's a double vector, then global double pointer pointer to a memory that is located inside the GPU. And then expression just delegates the work to its terminals. So if we have a binary operation and we wanted to declare its parameters for the kernel that we generate at the time, it just asks its left child to generate to declare parameters, and then it asks its right child to generate parameters, and then we are done. And if we want to build a string representation for the expression to put inside this inside this loop inside the kernel, we just change slightly our plus struct. So now we have a toString member that just returns this string containing a plus that we want to put into the source code. And then again, each terminal knows what to put into the expression string, into the expression representation of the global expression that we are building. And then each binary operation, it just puts an opening bracket, closing bracket, and it asks left child to do the work. Then outputs an operation that needs to be done, and then it asks the right child to do the work. So we have the complete expression encoded in a string. Now we can actually generate the source code. For example, here left-hand side and right-hand side are relative to the assignment operator. So we assign right-hand side to the left-hand side. Okay, so yeah, we declare some output string. We output the common header for the kernel. So it's just kernel void, some name. N is just the size of the vector. It always will be there. Then we declare parameters. Here I use, since I need to know the position of the parameters to name them, I just provide this outside position variable, which is taken by reference here and increased in each of the terminals. So here we declare parameters, another boilerplate code. This is a closing bracket for parameters, opening bracket for function body. This is grid stranded loop. Then we ask the left-hand side and the right-hand side parameters to declare the expressions. So we generate this expression that should be to the left of the assignment operator, and then we generate the expression that should be to the right of the assignment operator. And we are done. We have generated our kernel, right? We just return the source code, and then we compile it. Yes, setting kernel arguments is easy as well. We have this set arguments method. Yeah, but now it has to be, we cannot do this static because in order to set the actual arguments, you have to know the actual, you have to have reference to actual objects that will be sent to the GPU, right? So now each terminal again sets its own argument for the kernel with this OpenCL API call. Then each expression just asks its children to do the actual work, and then we are done. So to glue it all together, we again the magic happens inside the assignment operator. So when we want to assign to our GPU vector an expression of type expr, we create a kernel. So we call this kernel source function with this type and export type as template parameters. We build the kernel for the device we are currently on. And when we cache the compiled kernel inside this local static variable, so we don't have to generate it again and to compile it again, which is really time consuming, especially compilation. And then we set the kernel parameters and enqueue the kernel for asynchronous execution to the device queue. And then we are done. We have this kernel in the queue. It will eventually be executed, and we will have our results back. Okay. I already covered this. So yes, due to this trick with the local static variable, the kernel is only generated and compiled once and applied each time. And we can do this because this kernel only depends on the type of the expression that you have as an input parameter. So when you call this assignment operator with different type, it will generate different kernel, and it will be cached in local static variable of a different instance of this assignment operator. Okay, but actually what I just discussed is a bit too simplified, because there are other operation types besides binary operation. There are unary operation, n-ary operations, such as function calls, lazy function calls. Then there are some special terminals aside of the vectors that require some other treatment. For example, for some terminals, you need to declare some helper functions before you actually start to build in your kernel. And there are some also local preambles, like with temporary variables. You have to store some expression into the register, and it all gets very complicated and cumbersome if you do this with this technique. It's possible, and VexCL initially was created just with what I showed you, but then I decided to switch to Proto, and Boost Proto, and it really made my life much more easier, because Boost Proto is a framework for building embedded domain-specific languages for C++, and it does all this boilerplate work of overloading operators and of building these expression trees for you, and you only have to provide some code to actually evaluate the expression trees that you have. And here is an example of a very simple Boost Proto program. You just include this header, then you create an expression from this, and you need this as export to infect the expression with the Boost Proto operators. So this as export 6 becomes a terminal, a Boost Proto terminal, and Boost Proto terminals have all overloadable operators in C already overloaded. So when you multiply this terminal 6 with 7, you just get expression which says that you want to multiply 6 and 7, but does nothing at this time. Okay, and then, for example, you can display this expression, and it will show this tree structure for you, and you can also evaluate the expression, and you do this by providing a context. And the default context in Boost Proto just returns whatever is inside the terminal. So it will just do what you would think it would do. It will just return the number 40 as a result. And if you want to do some more advanced work with Boost Proto, you have to provide your own Boost Proto context, right? And you do this by defining this struct, which has several specifications of this template eval, and it just so for example, here we want to build a textual representation for an expression, and we take an expression as a first argument, and we take a context as the second argument. And this context is actually the copy of the global context that you provided to Proto eval function. So here we just do the same thing that we did with the basic implementation. We output some boilerplate code, and we ask our children to do the work within the same evaluation context. And this is for expressions with tag plus. You can also create specify this template for other tag types, and you also have special template specification for terminals, and each terminal just evaluates itself with a default context and outputs the value to the output string. So from this expression, if we evaluate it with this custom context, we will get a textual representation of the expression on the output. So this is the same way the source code generated in VexCL. And yeah, so for example, you just specify this, you create this global template, partial vector expression, and by default, it just outputs parameter with a number to the output stream. And then you can provide custom specifications of this struct for different terminals, for terminals of different type that have more than one parameter probably that should be defined for the kernel. And yes, so inside this print expression context, you use this template, you ask it to output the string for the specific type or expression type that we got. And you don't have to touch this context code anymore. You only have to provide these specializations of this template for your different terminal types. Okay, so and yeah, if we evaluate our expression with this context, we will get this parameter 1 multiplied by parameter 2 plus parameter 3. So this is the code that you can actually feed to a compiler if the compiler knows already what are these parameters. So this code is now very close to what is actually used in VexCL. So we can, we don't touch our contexts anymore because we have provided some boilerplate code, and we only have to, for each of the terminals, we provide instantiations of this special template which know what to do with this specific terminal type. Okay, and then we need some more context to be defined aside from this print expression context. We have to know how to define kernel parameters. We have to know how to set kernel arguments, etc., etc., etc. But basically, it's what is done in VexCL. So here's the general structure of OpenCL code. So here we have some custom function which returns double, which is named square, which takes 2 double arguments, and which returns square distance from squared magnitude of the vector. Then we have some temporary variable. We have this expression that we want to generate this kernel from. So inside the OpenCL code, for this function, we need to define this OpenCL device function. For each of the expression terminals, we need to provide a parameter. Then we have this grid striding loop, and inside the loop, we have to declare this temp variable to initialize it with this parameter, and then we just apply the expression to the output vector. So each terminal should tell VexCL how to use it. It should tell if it needs global preamble. For example, here with the function, we need to define some helper function to use it inside the kernel code. Each terminal should tell VexCL what kernel parameters it actually uses. Does it need local preamble, as is the case with this temporary variable, and how to build the expression from this terminal. Okay. So here is a simple example of the simplest terminal that you have in VexCL. That's an element index which just returns the position of the current element inside the vector. Okay, so we can use it, for example, as this. We can assign to X a wave which is generated by multiplying element index by 2 pi's and divided by total number of elements in the vector. So it's just a single period of a sine function. So in order to To use this terminal inside VexCL, we have to provide this struct element index, which keeps, well, we can provide an offset here so that element indexes do not start with 0, but with some arbitrary offset. Then, and you keep it inside the struct. And you have to here's this helper function that just infects this struct with a Boost Proto framework. So it just takes an offset and returns an element index, this struct with this offset, and it tells VexCL that this expression will be part of a vector domain. So you will only have to be able to mix these terminals with other vector expressions, but not with, for example, multi-vector expressions that are also part of VexCL. And then, we just tell VexCL that it can actually use this struct inside expressions. So you will, if you don't do this, you will get compilation errors. So if VexCL does not recognize your terminal. And then we do parameter declaration. We just want to, we have single parameter, which is offset. We feed to the kernel. Yes, and when we build an expression string, we just output its parameter name to the expression, the offset, right? And we then add it plus, we sum the offset with the index of the current element inside the kernel. Yeah, the kernel arguments are set in a similar way. We just want to send an offset to the kernel as an argument. And that's it. So element index is now fully defined, and we can use it in arbitrary vector expression. We can combine it with other kinds of expressions. And so actually now that we have this expression template engine, adding new terminal types becomes very easy. You only have to specify several templates and you are done. So there are some other uses for expression templates in VexCL. For example, these device filters, they may be combined, and these are also lazy functions. So this is a functor that takes a device and returns a Boolean, depending on whether you want this device or not in your context. And you can combine it with other filter, with this logical operator. And what this operation does for you, it creates another functor, which also takes a device, and it just delegates the work to the its children filters. So it's also, this technique also uses expression templates. And also there are symbolic variables, which you can use to record a generic C++ algorithm to get a source code out of it. So if you define an instance of a symbolic type and you apply some arithmetic operations to the type, to the instance, it does nothing except that it dumps the arithmetic operations it is being subjected to the output stream. So for example, if you declare two symbolic variables, x and y, and you initialize y with 6, and then you assign sine of 7 times y to x. On the output stream, you get this source code. So this is declaration of x, this is declaration of y, and it's also initialized with 6. And then this is the operation that you subjected the variables to. So now you can take some generic algorithm, for example, boost or the int algorithm. You can feed these symbolic types to the algorithm, and you will get the steps that the algorithm took written in the output stream. And now then you can compile the output, and you get the kernel that does the same thing that your generic C++ algorithm did with normal floating point types. right? Yeah, so here in this case we create a generic functor which just again returns a squared magnitude of a vector, and we feed this functor to this make function meta function. So this what this make function does, it has this signature, so it can create symbolic variables of appropriate types, and it can feed the instances of these types. So it's symbolic double and symbolic double. We call this functor with these types, and it will record this operation, and then we generate a function out of it. But this is a very simple example, but you can do some interesting stuff with this. The only restriction is that since you cannot overload conditional operators in C++, like if and while and for, so the algorithms that you can record has to be embarrassingly parallel, and there should not be any data-dependent loops or conditionals. So, but if you satisfy this condition, then you can create very effective kernels out of it. So, yeah, for example, here you see that we used the boost ODInt to do the parameter study of a Lorentz system. So we solved a lot of ODEs, ordinary differential equations, at the same time on a GPU. And we did this with different backends that ODInt provides. So for example, Kublas, it has BLAS interface with a fixed API. So you only have a fixed number of functions. And do we have enough time? Yes, so we solved this system, Lorentz attractor system, for a large number of parameter R, for example. And we use boost ODInt. And with the problem with Kublas is that it only provides you these functions that take a couple of vectors and return a vector to you. So for example, boost ODInt uses these linear combinations in its internal code. And if you want to use Kublas to encode this sequence, this linear combination, you have to split it into small sub-expressions. So you have to initialize the output to 0, and then you can subsequently add another term in this linear combination to the result. And the problem here is that you have to store these temporary results into a global memory of GPU. And again, the memory is the biggest bottleneck in all of the modern architectures. So when you touch the global memory, your code immediately becomes slower. And so this problem can be solved with, for example, Thrust library, which also works on CUDA. You just create a device functor, which takes 2 arguments and returns these linear combinations of the argument. And for each of the linear combinations, so it's if you have a linear combination of 2 elements, you have this scale sum 2 device functor. If you have 3 elements, you will provide scale sum 3 functor. And then you just apply this functor to the input vectors with the thrust for each algorithm. And this results in a single fused kernel that does not store any intermediate results into the global memory. So this is about 1.5 times faster than Kublas. And also we can do this with VexCL. You just say that you want x0 to be assigned to a1 times x1 plus a2 times x2. And this kernel that is generated here will be equal in performance to this Thrust kernel. And with VexCL symbolic implementation, you take this approach to the next level, because again, with either Thrust or VexCL, this naive implementation, there is another problem. You just fused your linear combinations into a single kernel, but boost ODInt internally uses several such linear combinations. So, for example, fourth order Runge-Kutta algorithm uses 4 intermediate steps that are encoded as these combinations. So each time you have to again store these intermediate results into global memory, and it's again, this is slow. So what you can do is you can pass VexCL symbolic variables to a boost order int algorithm, and then you launch, perform a single integration step of this of order int, and as a result you get a kernel that performs a single Runge-Kutta, single but complete Runge-Kutta iteration. Okay, and then you just execute this kernel as many times as you need to finish your experiment. And so no temporary variables are now stored into the global memory. They are now located inside registers for each of the threads that you run, for each of the individual ordinary differential equations. So here's again, this is what you get out of this. So this kubeless approach, although kubeless is very highly optimized library, which is provided by a vendor, by CUDA. So the kernels are really as fast as they can be, but just because it uses these intermediate variables that are stored in global memory, it's about 1.5 times slower on either Thrust or VexCL. And Thrust and VexCL show similar results on the same GPU. And then when you use this monolithic kernel generated with symbolic variables, you get 10x acceleration with respect to the either VexCL or Thrust. So it's like 15 to 20 times faster than kubeless. And kubeless is about 10 times faster than your CPU. So it's like 100 times faster than CPU. But it's not really fair because you can use the same approach for the CPU as well. You can do each individual integration completely on cache, and then this problem goes away for the CPU as well. So you get 10x acceleration when you use this approach, either on CPU or on GPU. And that's because memory is slow. Processors are fast. Okay, that's it.
While we are at it, have you tried OpenCL for the CPU?
Sorry?
There is SDKs which can execute OpenCL applications on the CPU.
On CPU. Yeah, we did try that, and it's let me see if I have I want just to show you the comparison of performance of OpenCL on CPU and on the GPU. Oh, I don't need that too. Okay. Yeah, so here's the results where you can compare the CPU with the OpenCL, I think. So this is a little bit more advanced plot of these same results, but with a number of equations that you are solving. And this is the absolute time that you solve these number of equations in, and this is relative acceleration with respect to kubeless. Okay, so this is kubeless, this is VexCL, and it's about 1.5 times faster here for really large problems, but for smaller problems, it gets slower than kubeless because of this overhead I was talking about in the beginning, because OpenCL has to compile its kernels at runtime, and it takes some time. So it's not as effective for small problems as CUDA, okay? And with Trust, you get the same performance in the end, but it's much faster here for small problems because it has less initialization overhead than OpenCL. And if you run the same problem with OpenMP, it's about 10 times slower than kubeless here, but as you can see, it outperforms any of the GPU frameworks for smaller problems. And so this problem with OpenCL with high overhead is not really important, because for these small problems, you just don't want to use GPU at all. You want to use CPU. And if you, this is OpenMP. If you use OpenCL, it will get about the same performance as OpenMP here for the large problems. But here it will be, I think, it will be actually slower than VexCL on CPU because it has same overhead, initialization overhead. It has to compile the kernels, but now for the CPU, and then it has to run the kernels. So for really large problems, you don't almost see no difference between OpenCL and OpenMP. And for small problems, you do see the difference due to this initialization overhead. Okay.
Do you transform the expression trees somehow?
No, I don't do that. I just, yeah, I let user do the smart things with the expressions. Karsten.
Maybe you mentioned it already. What was the reason to have a separate CUDA backend next to the OpenCL?
Because CUDA has a lot of libraries, and yeah, you can use VexCL with existing libraries easily, because when it's OpenCL, it's just based on Kronos C++ bindings. So you can use it, for example, with Boost Compute, with VMCL, with CL Blast, etc., etc. And CUDA also has a lot of libraries that you would like to use at some point. For example, you can use QSparse with VexCL or kubeless with VexCL kernels if you want to do some dense arithmetics and you know that kubeless will be just faster than these generated kernels. And also, it turned out that CUDA backend works better on NVIDIA hardware for some reason. No, just a bit faster.
You said that you paid more attention to memories because to memory access because memory allocation is cheap, relatively because it's constant, but it's still expensive. And
yes.
And especially on a GPU, it's ridiculously expensive. So I made this experience. Just having a few temporaries took more.
That's another point to not using temporaries, right?
No, I think it's another point to using temporaries. So it's not only for having less memory access. It's also to avoid these temporaries, especially on a GPU. It's so ridiculously expensive.
Yes, I agree.
And you know this.
You mentioned an integration where you used a fixed time step, I think. Have you any experience with adaptive time step algorithms?
I think we have a possibility to use adaptive time step with ODINT, right? Because Karsten is the author of ODINT. And
yeah, but on the GPU especially, where you want to parallelize.
Yes, we did some. There is support for adaptive time step on GPU.
You have no practical experience, because I think it's kind of strange to have.
Well, you cannot record a kernel with these symbolic types, but you can use this naive approach with ODINT and it will work.
Have you encountered expression trees where you have to launch more than one kernel?
Sorry?
Have you ever seen an expression tree generated that requires you to start more than one kernel?
Well, I have some parallel primitive that require that. For example, fast Fourier transform launches more than one kernel because it's several transformations, and the matrix vector product also requires you to launch several kernels, especially if you run on different GPUs, several GPUs, because you need to exchange boundary values between the GPUs. So you have to do the internal work, wait for the completion of the exchange, and then do the additional step that finishes it for the external data. So some of the expressions are not do not result in single fused kernel, but most of the time they do.
About conditions, is conditions just beyond this presentation, or do we limit to don't use any conditions in VexCL?
What kind of conditions?
Some if statements in any kinds, or
Yeah, the restriction about if statements were about this usage of these symbolic types. So these symbolic variables, they overload all possible operations that are overloadable in C++, but you write here, for example, if x is less than 0, then do something with y. It will not work because you will only get one branch of this if. It will get recorded, but not as if, but just as several steps, because if is not overloadable in C++. You cannot do anything with it. Is that clear?
okay, it's clear. So we did a workaround for this, but I don't remember because it doesn't colleague. So for SIMD programming, so where we have some different types.
Okay, maybe we can talk later.
Yeah.
I think Boost Fusion provides some expressions that do the same thing that conditionals do, but with if underscore, while underscore. So it's you have to use these special expressions to do this.
Yeah.
Not native conditionals.
Yes, sure. So you have to work around. So this
Yeah.
was the question.
Okay. Thank you.